With every passing second, billions of decisions are made in absolute silence. These are not choices made by human hands, but by invisible digital minds governing the infrastructure of our modern world, from global financial markets to the intricate webs of our power grids. This entity is not sorcery, nor is it a mysterious consciousness. It is an engineering marvel rooted in the physical realm, where quantum physics meets mathematical algorithms inside concrete fortresses that consume enough energy to power entire cities. To truly understand how AI makes a decision, we must look beneath the software and dive into the depths, where electrical pulses transform into thoughts and mathematical matrices become logical conclusions that mimic the human brain. It took us centuries to reach this moment, evolving from the mechanical gears of Babbage's engine to vacuum tubes, and finally to silicon transistors that have shrunk to the scale of a single nanometer, allowing for unimaginable computational density. While the biological brain relies on chemical reactions between neurons and electrical signals, its digital counterpart depends on a rigid architecture of logic gates and high-precision arithmetic that never tires. The journey begins with a simple touch or a voice command. In that instant, your human intent is distilled into a digital data packet, encrypted and ready to race at the speed of light through the air toward the nearest cell tower. The signal pierces the atmosphere, captured by the phased array antennas of 5G towers, where electromagnetic waves are instantly converted into pulses of light. These pulses travel through underground fiber optic networks, crossing oceans via subsea cables shielded by layers of steel and polyethylene to withstand the crushing pressure of the deep, all while carrying millions of simultaneous requests racing toward the central processing mind. These digital pathways converge at a single point, a hyperscale data center. Here, data is received at the main gateway, facing the first lines of defense and sorting before being granted entry into the inner sanctum of processing. Security here isn't just about guards and gates. It consists of firewalls and encryption algorithms that inspect every packet in a microsecond to ensure its integrity. A load balancer receives the request, analyzing current traffic and directing the data to the least crowded server to ensure the lowest possible latency, a coordination effort akin to managing a bustling international airport. We now reach the physical unit, a slim server housing advanced C, P, U, S, and G. P, U, S. This is the body inhabited by AI, a metallic skeleton designed to dissipate heat and provide stable power. Before any calculation begins, high-voltage alternating current from the grid must be converted into ultra-stable direct current, as even the slightest voltage fluctuation could cause catastrophic errors in precision calculations. Electricity flows through copper pathways etched onto multi-layered printed circuit boards, reaching the heart of the system, the GPU or the TPU. We are looking at a sliver of silicon no larger than a few square centimeters, yet it contains tens of billions of transistors. Each one acts as a microscopic switch, flipping billions of times per second. These chips are manufactured using extreme ultraviolet lithography, an engineering process that touches the very limits of physics, etching paths smaller than a virus to allow electrons to pass. As the math begins, immense heat is generated by electrical resistance. If this heat isn't dissipated immediately, the chip would melt in seconds, requiring a decisive physical intervention. To prevent this, a liquid cooling system pumps dielectrically stable fluids directly over the processor's surface to absorb the heat and carry it away to heat exchangers, keeping the silicon within a safe operating range. Right next to the processor sits the HBM, or high bandwidth memory, ultra-fast data reservoirs that allow the processor to recall necessary information thousands of times faster than traditional memory. With the hardware stabilized and the power ready, we leave the tangible world and enter the abstract, logical realm, where the true data journey begins within the complex architecture of an artificial neural network. The first step in logical processing is tokenization. The system does not understand human words. Instead, it breaks text into small units and converts them into integers that represent their identity in a massive dictionary. These numbers are then transformed into embeddings, mathematical vectors that place the word in a multidimensional space. Here, words with similar meanings are mathematically and angularly close to one another. These vectors enter the first layers of the neural network, where massive matrix multiplication begins. Every number in the input is multiplied by weights learned during the training phase. Imagine an artificial neuron as a mathematical function. It receives multiple inputs, sums them up, and adds a bias value. This sum determines the importance of that information in the context of the final decision. To decide whether a neuron should fire, the result passes through an activation function, such as RELU, U, which discards negative values and keeps positive ones, adding nonlinearity to the system. At the heart of modern systems lies the attention mechanism. This allows the model to focus on specific parts of the input while ignoring others, much like how you focus on a single voice in a noisy room. Multi-head attention calculates the relationships between every word in the text to understand deep context, knowing, for instance, that the pronoun he refers to the person mentioned at the start of the sentence. This process repeats across dozens of deep layers. With each layer, concepts become more abstract and complex, moving from simple character recognition to understanding grammar, and finally, grasping intent and meaning. These operations occur in massive parallel across thousands of cores in the GPU, executing trillions of floating-point operations per second, or FLOPS, to produce a single response. At the end of the network, the system doesn't give one definitive answer. Instead, it generates a probability distribution for all possible next words. It weighs the options. Is the next word happy with a 70% probability or sad with 5%? Here, parameters like temperature intervene to determine randomness. A low temperature makes the system choose the most likely word every time, while a higher temperature grants it the creative freedom to choose less predictable words. Once the winning token is selected, it is decoded back into human text and added to the conversation context to generate the next word. This process is called autoregression. The system writes the first word, reads what it wrote, decides on the second, and continues building sentences and ideas, piece by piece, in a continuous feedback loop. What we see now is the inference stage, but it relies entirely on a training stage that lasted for months, where the system slowly adjusted billions of weights to minimize error. During training, the system used an algorithm called backpropagation, a mathematical process based on calculus to calculate the error gradient and adjust the strength of neural connections. After general training, the system undergoes fine-tuning using RLHF, or reinforcement learning, from human feedback to polish its responses and make them safer, more helpful, and aligned with human values. However, a major constraint is the context window. The system's working memory is limited. If the input exceeds a certain limit, it begins to forget the start of the conversation, requiring advanced compression and memory management techniques. Sometimes, the algorithm fails to find a factual pattern and invents incorrect information to fill the gap, a phenomenon known as hallucination. The system isn't lying on purpose. It is simply completing the most statistically likely pattern, regardless of the truth. To combat harmful outputs, a final supervisory layer acts as a sensor, scanning the generated text for profanity or dangerous content and blocking it before the user ever sees it. After passing all these tests, the final answer is bundled into a data packet, and the physical journey reverses. Data exits the memory, passes through the processor, and hits the network card. It leaves the server rack, moves through switches that direct it toward the data center's external gateway, and heads back out into the global internet. In a fraction of a second, the answer travels thousands of miles back to you, appearing on your screen as if from nowhere, the result of a complex dance between energy, matter, and mathematics. But this process isn't free. Every query consumes electricity, and every decision leaves a thermal and carbon footprint, posing massive environmental challenges as these systems expand. What happens if the power suddenly cuts out? Data centers are equipped with arrays of backup batteries and massive diesel generators that kick in automatically to ensure the thinking never stops for a single moment. In the event of cyber attacks, such as DDoS attacks, intelligent defense systems analyze traffic patterns and isolate suspicious requests in digital black holes to protect the infrastructure. To ensure continuity, data is replicated and models are distributed across multiple geographic regions. If an earthquake hits a data center in California, a facility in Virginia takes over immediately, without the user ever noticing. To make these systems more efficient, engineers use quantization, reducing the precision of numbers from 32-bit to 8-bit or less, which speeds up calculations and reduces memory consumption without a significant loss in intelligence. Sparse models are also being developed, where only a small portion of the neural network is activated for a specific request, rather than running the entire giant network, mimicking the efficiency of the human brain. The future promises revolutionary technologies like optical computing, which uses photons instead of electrons to perform calculations, promising radical increases in speed and reductions in heat. Then there is neuromorphic computing, which attempts to mimic the physical structure of the biological brain, merging memory and processing into a single unit and bypassing the classic bottleneck of von Neumann architecture. Perhaps the greatest leap lies in quantum computing, which will enable us to train models and solve complex optimization problems that would take today's most powerful classical computers millions of years. Today, this digital nervous system has become an inseparable part of the fabric of our lives. It decides which news you read, how your self-driving car moves, and even provides initial medical diagnoses. In medicine, these networks analyze MRI images with precision exceeding that of the most skilled doctors, detecting subtle patterns of tumors in their earliest stages and saving thousands of lives daily. In the economy, high-frequency trading algorithms execute millions of trades in fractions of a second based on real-time data analysis, moving trillions of dollars without direct human intervention. Cities are transforming into intelligent organisms, where AI systems manage traffic lights, electricity, and water grids, adapting instantly to demand to reduce waste and improve quality of life. We are not just building faster calculators, we are building a cognitive partner. This decision-making system is an extension of our mental capabilities, freeing us from routine tasks and opening new horizons for creativity and discovery. AI has begun writing its own software and designing its own chips in an accelerating cycle of self-improvement that may soon lead us to what is known as the singularity. But with this power comes immense responsibility. How do we ensure these systems remain biased in favor of humanity? How do we prevent the bias latent in data from magnifying into systemic discrimination? The black box problem remains. Even the engineers who built these systems cannot always explain exactly why a network made a specific decision, creating challenges in trust and legal accountability. Therefore, researchers are now developing explainable AI, or XAI, tools aimed at illuminating those dark corners within the network to explain why the machine made its choice. The quality of decisions depends entirely on the quality of data. If we feed the system biased historical data, it will repeat the mistakes of the past with higher precision and frequency. Thus, data cleansing is the most important ethical step. In the judicial system, AI is used to help analyze cases, but total reliance on it raises fundamental questions about justice and mercy, two human qualities that are difficult to translate into code. In the military sphere, lethal autonomous weapons systems raise deep ethical concerns. Should an algorithm be allowed to make a life or death decision on the battlefield without human intervention? On the bright side, these systems can democratize education, providing a personal tutor for every child in the world that adapts to their pace and learning style, breaking the barriers of poverty and geography. They can also help farmers optimize crops and reduce water and pesticide use, contributing to solving the global food crisis and facing climate change with unprecedented intelligence. Systems like AlphaFold solved the protein folding problem that baffled scientists for 50 years in just a few weeks, opening the door to medical treatments we once only dreamed of. Even in the pursuit of clean nuclear fusion energy, AI plays a crucial role in controlling unstable plasma, bringing us one step closer to infinite clean energy. The complexity of the modern world has exceeded the capacity of the unassisted human mind to manage optimally. We need these assistive systems to untangle global supply chains and prevent economic collapses. We are witnessing a merger between biology and technology. Silicon and carbon are no longer separate worlds. They integrate to form a new kind of hybrid intelligence leading the planet. When a request ends and the circuits cool slightly, the system remains in a state of constant vigilance. Stillness here is a deception. The readiness for the next operation never stops. It is a mind that never sleeps. Let's take a step back to the smallest unit, the transistor. When we say 1 or 0, we mean high or low electrical voltage. This binary language is the physical foundation of all this complexity. Transistors cluster to form logic gates like A, N, D, O, R, and N, O, T. These simple gates combine to form addition and subtraction circuits, which in turn build complex arithmetic logic units, or ALUs. All these operations are paced by the processor's clock speed, where a crystal oscillator sends pulses billions of times per second to ensure data movement is synchronized across the chip. Processors also use pipelining, where one instruction is fetched, another is decoded, and a third is executed simultaneously to ensure no clock cycle is wasted. To feed this computational beast, there is a memory hierarchy, where level 1, 2, and 3 cache store the most frequently used data very close to the processor to minimize wait times. When the processor doesn't find data in the cache, a cache miss occurs, forcing it to go to the slower RAM, which is an eternity on the processor's timescale. Communication between the CPU and the GPU happens via high-speed PCIe lanes. Bandwidth here is critical. Any bottleneck in this lane will slow the entire system, regardless of the processor's power. In AI servers, multiple GPUs are linked together using special interconnects like NVLink, allowing them to function as a single giant brain and share memory at incredible speeds. Mathematically, the learning process is an attempt to reach the lowest point in a multi-dimensional valley. The gradient descent algorithm guides the model step by step toward the optimal solution to minimize error. The size of the step in this descent is determined by the learning rate. If it's too large, it might overshoot the solution. If it's too small, training will take far too long. Tuning this rate is both an art and a science. However, one risk is overfitting, where the model memorizes training data by heart instead of understanding general patterns, failing miserably when facing new data. Conversely, there is underfitting, where the model is too simple to capture the complexities in the data, leading to shallow and inaccurate decisions. To prevent this, we use techniques like dropout, where we randomly turn off some neurons during training, forcing the network not to over-rely on a single path. Batch normalization also helps stabilize learning by readjusting the outputs of each layer to be within a certain range, preventing numbers from exploding into astronomical values or vanishing to zero. In image processing, we use convolutional neural networks, or CNNs, which pass small filters over an image to detect edges, then shapes, then complex objects, mimicking the visual cortex of the brain. For sequential data like audio, recurrent neural networks, or RNNs, were once used. They possessed short-term memory, but suffered from forgetting distant information, which paved the way for transformers. Since transformers process data in parallel, they need positional encoding to know the order of words in a sentence. Otherwise, the meaning derived from linguistic sequence would be lost. In the final layer, a softmax function converts the raw scores, or logits, into relative probabilities that sum to 100%, making the result interpretable. When generating text, the system doesn't just look at the next word. It might use beam search to explore several potential future paths and choose the one that yields the best overall sentence. Among the most remarkable capabilities of large models is zero-shot learning, where a model can solve tasks it was never directly trained on, simply due to its deep understanding of relationships in data. We are now moving toward multimodal AI, which doesn't just read text, but sees images and hears sounds, merging all these senses into a unified understanding of the world. Even storage has evolved. NVMe SSDs provide the blistering read and write speeds necessary to load massive models that reach terabytes in size in just seconds. Since cosmic radiation can flip a bit in memory, servers use ECC, or error correction code memory, which detects and corrects these spontaneous errors to prevent data corruption. On the software side, applications are wrapped inside isolated containers managed by systems like Kubernetes, allowing thousands of instances of the system to run and scale with immense flexibility. Systems talk to each other via APIs, the common language that allows an app on your phone to speak to a server on another continent, exchanging data in structured JSON format. All this communication is protected by TLS encryption protocols, where keys are exchanged at the start of a connection to create a secure tunnel. The greatest enemy is latency, so engineers fight to reduce delays by the microsecond, placing edge computing servers geographically closer to users. Content Delivery Networks, or CDNs, store cached copies of data in hundreds of locations worldwide to ensure content reaches the user from the nearest point. To maintain privacy, federated learning is emerging, where a model is partially trained on your own device without sending your personal data to the cloud. Only the mathematical updates are sent. When you look at the full picture, you see a symphony of hardware, software, mathematics, and physics working in stunning harmony. Every part, no matter how small, plays a vital role. Yet, in this complexity lies fragility. A single failed capacitor on a motherboard can take an entire server offline, which is why redundancy is key to engineering design. Storage systems use RAID techniques, where data is written across multiple disks. If one fails, the lost data can be reconstructed using parity information. Companies use chaos engineering, intentionally cutting cables and shutting down servers to test the system's ability to self-heal. Security-wise, the system faces new challenges, like prompt injection, where attackers try to trick the model with hidden instructions to bypass safety controls. There are also adversarial examples. Tiny changes in image pixels invisible to the human eye, but enough to fool an AI into classifying a panda as a washing machine. A future risk is model collapse. If AI begins training only on content generated by other AI, quality degrades, and models lose their connection to reality and human diversity. To distinguish machine-made content, watermarking techniques are being developed to embed hidden statistical patterns. Systems must also comply with global privacy laws, like GDPR, where strict rules are programmed to ensure a user's right to be forgotten. To improve sustainability, some data centers have begun recycling the immense heat generated by servers to warm nearby homes and buildings. The open-source movement plays a pivotal role, providing powerful free models to developers worldwide, breaking the monopoly of tech giants. AI is no longer just a data analyst. It has become a creator, painting, composing music, and writing poetry, sparking philosophical debates about the nature of creativity. The ideal relationship is not replacement, but augmented intelligence, where humans and machines work together. Humans provide intuition and values, while the machine provides computational power and speed. We may soon see direct brain-computer interfaces, eliminating the need for screens and keyboards. In space exploration, where communication delays are vast, rovers rely on AI to make navigation decisions on Mars. Digital twins of entire cities and factories are being created, simulations that allow us to test disaster scenarios in the virtual world before they happen in reality. Materials science is witnessing a revolution as AI predicts the properties of new chemical compounds, accelerating the discovery of better batteries and solar panels. Personalized medicine will become the standard, with drugs designed for your unique genome. Language barriers are falling, as accurate real-time translation allows people from different cultures to communicate seamlessly. Reducing waste in food chains through precise demand forecasting can feed millions. The efficiency provided by these algorithms has deep humanitarian dimensions. However, we must be wary of deepfakes. The ability to generate realistic video and audio of public figures poses a real threat to truth and stability. An arms race continues between fakers and detectors, where digital authentication and blockchain may be the solution. The cost of training these models is staggering, reaching hundreds of millions of dollars, raising concerns about the concentration of power. Therefore, nations are striving to build sovereign AI, independent, national infrastructure to ensure data security. Education must change. AI literacy has become a necessity. We must understand how these tools work to use them effectively. We return to the philosophical question: can a machine feel? Currently, the answer is no. It mimics emotions based on linguistic patterns, but lacks subjective experience. The ultimate goal for some is AGI, or artificial general intelligence, a system with the flexibility of the human mind, still a distant dream and a subject of intense debate. Protecting privacy in this era requires smart legislation and advanced tech like homomorphic encryption, which allows data to be processed while encrypted. In natural disasters, drones analyze images of stricken areas to locate survivors, making the difference between life and death a matter of precise algorithms. In aging societies, AI-powered robots may provide companionship and care. The volume of data we produce daily is measured in exabytes, and AI is the only tool capable of sifting through this flood to extract wisdom. From the ocean floor to the silicon atom, from the mathematical equation to the user interface, we find a linked chain of human innovations that have accumulated to create this technological miracle. This system is not just a tool, it is a new cognitive infrastructure for the planet, a layer of intelligence surrounding the Earth. Future generations will look back at our era as the moment we taught the sand to think, and how that changed the course of human history forever. In the end, Inside that black box, as the lights flicker in the dark, the machine continues to work, decide, learn, and evolve in a profound silence that carries the weight of our collective future. This has been a journey into the depths of artificial intelligence. Remember, technology is neutral. We are the ones who determine whether to use it to build a better world or to destroy it.